All right, so we are going to take a little bit of time to review some of the important things that you need to know about objects in free fall. First, it says here that free fall is the motion of an object under the influence of gravity alone, and they are asking us to ignore air resistance. So I want to pause right here and make sure that everybody knows what that means. Whenever we are neglecting air resistance, ignoring air resistance, or if we are told that air resistance is negligible, that means we answer as if there is none, okay? In most or many real life scenarios, the air resistance is not great enough to actually create an effect. So I want you to imagine dropping a very dense object, and that's going to be how we're going to handle all of our answers. Okay, so neglecting air resistance, ignore air resistance, answer as if air resistance has no effect on the object's motion. The second thing that we want you to remember is that these objects are subject to gravity and gravity only. If we are ignoring air resistance, then the only other thing that could possibly be acting on our object is gravity. Now, you may have learned prior to this class that gravity is a force that has the ability to pull things down towards the earth. That is a true statement. In this chapter, we are not evaluating forces, but understanding that that force is the reason that the object is accelerating is very helpful. You should have learned that acceleration, by definition, is a change in velocity that occurs over time. So understanding that gravity is causing my object to accelerate towards the earth means that my object is experiencing a change in its velocity with every second of time. For falling objects, for objects that have been dropped, this means that my object is going to change its velocity so that it's going to move faster and faster as it falls down to the ground. Notice that it says here all objects are going to experience this acceleration rate. Now, the phrase in its entirety is acceleration due to gravity, but we like to shorten things, so we're going to shorten this up and we're just going to refer to it as gravity. It is an acceleration, but we could write this as A with a subscript G, where that subscript is telling me specifically the gravitational acceleration. And because it's an acceleration, we see that our units are in meters per second squared. When we look at this value, the way it's written here, instead of saying A for acceleration or AG, it's just expressed as the letter G, and you will see that from time to time. My value for gravity, or the acceleration due to gravity, is expressed as a negative 9.8 meters per second squared. Remember that acceleration is a vector, and in this case, it is expressed as a negative value because the acceleration is in the downward direction. When we look at our formulas that we have already received for kinematics, we see that we have lots of equations here that have an A for acceleration, and really, depending on the calculation, you could use any of these formulas as long as you plug in a negative 9.8 in place of that acceleration. But in this chapter, we are going to be using our displacement equation quite a bit. And so I want to point out a couple of things. In the vertical direction, or in the y direction, that's the direction that we are currently analyzing. So although we said that displacement can be indicated with an X, I don't want you to get confused. I want to make sure that you understand when we are talking about horizontal motion and when we're talking about vertical motion. So you may choose to give me a little vector saying that it's downward, or just a vector saying that it's vertical in general. You may choose to say that it's the displacement but in the y direction. I am going to give you this formula so that it has been altered specifically for vertical motion. So instead of saying delta x for displacement, I'm going to say delta y is equal to VIT plus 1/2 GT squared. If we are working in the vertical direction, my acceleration absolutely has to be gravity. So we go ahead and make it a G so that there is no question. It will always be a negative 9.8. this is an illustration of a girl dropping an object. And so if we read, it's telling us that the object is moving faster or speeding up as it falls. And we know this either because we understand the definition of acceleration, means that it's a change in velocity over time. Acceleration is a vector, which is downward. Velocity is a vector, which is downward. And so they are basically teaming up or joining together in order to increase that value for our speed or magnify that velocity. If you are a visual person, you may have noticed right away that these dots, which represent the location of my object at 1 second intervals, these dots are not spaced evenly. So between 0 seconds and 1 second, we have just a little bit of space between them. For the next time interval, we have more space, and then we can see that as the object falls, the distance between those dots gets bigger and bigger. Well, if we review, that velocity is that displacement over time, then it makes sense that if these values for my distance or displacement are increasing over time, then that means that my velocity is increasing over time. Here they've given you some values. So if you'll notice, we said that acceleration is going to be a negative 9.8 meters per second squared in this class. But for this particular illustration, rather than calculating with a negative 9.8, they decided to just round this off to give us an acceleration rate of a negative 10. And that basically just makes the numbers real nice and pretty, so it's easy to see this pattern. So when we say that acceleration is the change in velocity over time, what we're saying is that for every 1 second of time, my object is going to change its velocity in increments of negative 9.8, or for the purpose of this illustration, of negative 10. So we can see that our value changes from 0 to 10 to 20 to 30. Now this is technically showing me my speed because it does not clearly indicate that this is in the downward direction. But if we wanted this illustration to represent our velocities, we would simply put negatives here. Please remember that in physics, a value of negative 10 is not less than 0. This represents a velocity, a speed. So imagine that you're in your car and your speedometer is at 0 meters per second. How in the world are you going to go any slower than 0 meters per second? There's no such thing, right? You're not moving. You can't go any slower than not moving at all. So when we say negative 10, we are not saying that my object is going at a velocity less than 10. We are saying that my object has a speed of 10 meters per second while traveling in the negative direction. When you are asked to calculate the instantaneous velocity of a falling object, this most often will be the formula to use. And so I just want to take a second to make sure you understand what variable you should be solving for in this type of question. If you are asked to calculate the velocity for an object that is falling, or after it has fallen for however many seconds, 10, 30, 90 seconds of time, if the question wants to know what is the velocity of the object when it hits the ground, just before impact, as it reaches the ground, all of those questions are going to ask you to solve for the VF in this formula. Your VI stands for your initial velocity. So at the moment that the object is dropped, that would be your VI. Your VF is any point in time after that moment or during that fall. If we go back and look at my image of the object being dropped, whether you noticed it because the value was written or conceptually you understand that she's holding the object, my initial velocity here is 0, and that's actually going to be a true statement for all dropped objects. So when we look at this formula, I'm solving for my final velocity, and my initial velocity actually ends up substituting in as a 0, and I'm adding that number, so I'm adding nothing. So that part of the formula really just kind of goes away. For dropped objects, it's really just the acceleration rate of gravity and the amount of time that it's been falling. Minus air resistance, everything falls at the same rate. Now, I can tell you this over and over and over again, but for some of you, seeing is believing. For some of you, you need to visually experience this for it to sink in. So I have a couple of videos that I've embedded on the next slide, and then I have an additional video here. I would really like for you to get on YouTube and go find these videos, either by typing in the title that you see on the screen, or simply click on the link in the PowerPoint that is available on Canvas, and it will take you directly to those YouTube videos. But I want you to make sure that you are clear in understanding how to answer questions about objects that are dropped. So please take some time to go and view that. This is expressing the same main idea. All dropped objects are going to experience the same acceleration rate. So if it were a race, it would be a tie. They would have the same speed along the way. It doesn't mean that they have one speed the whole time, but it just means their values for how fast they're going would be identical. Okay. Now, the first part of this slide says in a vacuum. So let's make sure you understand what that means. A vacuum is a situation where we have eliminated all of the air molecules. So we have containers where the air molecules are actually sucked out of that container. So if there is no air, then there is no option for air resistance. And that means the only thing that could possibly affect the object that's inside of it is gravity. So when we say that we want you to answer these questions assuming gravity alone and ignoring air resistance, well, we can actually demonstrate what would happen if there was truly no air resistance. So that's what these two videos are there to illustrate for you. This video here about the coin and the feather, they actually create that vacuum environment. So that's kind of interesting just to see how that works as well. All right, a couple of questions are going to be worked out here. So first off, let's do one problem for objects that are just dropped straight down. I'm going to work through this problem rather quickly. So it says here that a stone is dropped from the top of a cliff. When you read that a stone is dropped, you should immediately know that we have an initial velocity of 0. And we understand that this object is falling. So that means we have an acceleration due to gravity of a negative 9.8 meters per second squared. Notice there are no numbers printed in that first sentence, but from reading that statement, I have two values that need to go on my list of givens. It is seen to hit the ground below after 3.55 seconds. And it says how high is the cliff the stone has been dropped from. So we are looking for that vertical displacement. Looking at our formulas to pick from, I have displacement here, here, and here. Now, these two equations are the same formula. It's just that the bottom one is written so that it's expressed in terms of vertical motion already. So looking at those two formulas, then down at the bottom between these two, I'm going to compare what I have on my list to what the formula is asking for. So this first equation, VF squared, is going to require me to know my VF, which is not on my list, although I do have all of the other variables. I'm going to look to see if I can use this displacement equation instead. So so Y is my unknown. VI is a variable on my list, and so is time. Plus 1/2, obviously I know gravity, and then time is on my list. So I have everything that this formula is asking for. My initial velocity here is 0, so this whole value will become a 0, so I'm adding nothing. So when I go to plug in my numbers, I am going to say Y is equal to 1/2 negative 9.8 times 3.55 squared. And that is going to give me a value of negative 61.7522. And there's some more digits in my calculator that I just won't write. So this formula is designed to calculate the displacement. My object fell so that it landed in the negative direction from where it started, a distance of 61.752 meters away. Now the question itself is asking me how high is the cliff. So it's actually asking for that vertical height measuring from the ground up. So my final answer here is going to be written as 61.8. Now, how did I know to round to the tenths place instead of making this a whole number? Remember that we are going to use all measured values that were provided in the problem that we ended up using in our calculation. So for this question, it's only 3 sig figs because that is the only measurement that I was given. We will not use the rate of acceleration due to gravity to determine our significant figures.